All right, well, welcome everyone. I'm going to share my screen and make sure that I think microphone should be working better this evening. So let's go ahead and see if I can share my screen successfully here. All right, what I'm putting up here on the screen is what is linked in the video description. There's not a whole lot tonight with respect to content in the Google document. So all of these links on this first page, these were all the links that were actually shared a couple of days ago, back on Saturday. And what I'd like to do tonight is to review free response questions. Okay, so we are reviewing free response questions, and I'm going to explain some common misconceptions that students might have. So the first link that is listed right here on this page that says AP Chemistry free response questions from previous years, if you were to click on that link, it would take you here. It would take you to the College Board, and it would basically give you free response questions from a variety of previous years. I'm going to start with 2024, and then I will eventually switch to 2023. But every time I go through a question, I will try to explain what the intended answer is, and then I will also show you examples of student misconceptions. So hopefully tonight will go pretty smoothly, but again, you all can let me know. Let me just double check and see if I can take a look on my, all right, this is a weird way to view it, but let me double check that. Let's see, I'm gonna just open up my, let's see, no, I can't do that. I'm gonna open up, just making sure that chat is running. All right, while I'm waiting for that to load, I'm gonna go over to my screen here. Okay, so we're starting with the 2024 AP Chemistry free response questions. And what I will do, let's see if I can draw successfully here on my screen. Okay, let's see. Excellent. Okay. So we're taking a look at the 2024 free response questions, and I'll just read the question. In some cases, I might just do a quick answer. I will also show you examples of student mistakes and misconceptions. So this particular question was intended to be just which of these hydrogens represents the one that would be participating in the acid-base reaction with sodium hydroxide. So that would be a mistake if a student tried to circle more than one atom. So let's see if I can go ahead and erase what's on my slide here. Erase all that drawing. Okay, so it's going to be this particular hydrogen right there. Okay, that was the intended answer. That happens to be part of a group called a carboxylic acid, and they discuss carboxylic acids in Unit 8 in topic 8.6 on molecular structure of acids and bases. And then the next part of this particular question is asking you to do a calculation. So it's a pretty simple calculation in that it says calculate the molarity. So we're looking for the molarity of the sodium hydroxide. So I'm looking for the number of moles of sodium hydroxide per liter. So what I would need to do is write down 10.22 grams of sodium hydroxide. And if you do the math, it's approximately 40 grams per mole. It's like 22.99 for sodium, plus 16 for oxygen, plus 1.08 for hydrogen. So that would get you that calculation right there. And then we're dividing by 500 milliliters, but no, we're not dividing by milliliters, we're dividing by liters. Okay, so that would be that calculation. Now I'm going to exit from this PowerPoint for just a moment. Okay, and what I'm going to do is on my computer, let me just double check and see if my chat was working here. Yep, okay, definitely. All right. Okay, so yes, with respect to the link, if you arrived late, there is a link in the chat, and we are taking a look at the 2024 FRQs, or free response questions, and then also the 2023. So in that Google document, and I can pull this up on my computer, the official scoring guidelines happen to be on my computer, but they're in that Google document. You can definitely take a look at them. So you can see on this view here, they're showing all of these answers here. I'll make this a little larger. So again, the intended answer for question number 1, part A of the 2024 free response questions was that particular hydrogen was circled. And now you can see that that number for the molar mass of sodium hydroxide is right there for part B. And you can definitely see that the intended answer was 0.511 moles per liter. But you'll notice that you don't need that number ever again. So it's lovely when on the AP chemistry exam, it's lovely when you don't need to continue to use the same numbers, because some students worry, what if I make a mistake in part B? Now it's going to mess me up for part C and D. The AP chemistry readers, they do a policy of what's called error carried forward. So if a number was incorrect in part B, but then that incorrect number was used correctly in part C, you would not lose 2 points for making one mistake. So, but oftentimes on the AP chemistry exam, when there's calculations, you don't necessarily carry over the calculations from one part to the next. All right, I am kind of revealing the answer to part C, so let me go ahead and go back to my PowerPoint where I have these questions. And this is part C of this same question. The student uses the sodium hydroxide solution. They're not telling you what that concentration is because they're not giving away the answer. A burette, a pH meter, and a 100 milliliter Erlenmeyer flask to carry out a titration experiment. So what do I need to look at in this particular titration curve? Well, it's right there in part C. Use the information in the graph to determine the pKa of lactic acid. Let me just double check and see if my drawing tools are turned on here. Okay, so what I'm looking at on this curve is that this right here is the location of the equivalence point. Okay, so that's 16. I cut that number in half. So this would be the half equivalence point. And then I'm going to estimate that that would be just under 4, so maybe approximately 3.9. That is my pKa of this acid that was titrated. All right, the next part of this question is a particle diagram that's related to this particular titration curve. So how is that particle diagram related? Well, if I go over here, this would be mostly molecules of HA. I'm just using the generic formula for a weak acid. And then at the equivalence point, we would have, right here, we'd have particles of A minus. So you're going from HA to A minus. All I really have to do is count the particles and decide whether we are exactly at the halfway point, in which there would be equal number of molecules of HA and ions of A minus. I don't think we're there. Or are we before or after the halfway point? Now, if you're wondering why are there black circles in there, well, it's because it was sodium hydroxide that was added. And so when the hydroxide ions are reacting, the sodium ions are just spectator ions, just hanging out in solution. So if I count the number of particles here, I see 1, 2, there's only 2 particles of A minus, but then I see 1, 2, 3, 4. Well, hopefully you can tell that because there are more particles of HA and fewer particles of A minus, that we are not at the halfway point. We're probably somewhere in this region right here. So I'm going to go ahead and show you what it says on my official scoring guidelines, but we have to put an X on the diagram, on the curve, where we think that reaction mixture would be. So not the halfway point, but somewhere, I would say around maybe 5 milliliters or somewhere in that range. And then it says justify your answer. So I would say something like, well, there is a greater number of HA than A minus. And so that's why we are before the halfway point in this titration. So now I'll just kind of show you the official scoring guidelines, which I think are still open here. Okay, and you can see that the correct answer would be that the X should be placed at a point somewhere between 3 milliliters and 8 milliliters, I would say around 5 or so. And then the justification, more acid particles are present than conjugate base. So there's more lactic acid, which was the weak acid that was being titrated, and there were fewer particles of the conjugate base, the lactate ion. All right, now I'm going to reveal the answer there if I keep going. So let me go back to the PowerPoint. We'll take a look at the next question. So remember how that student had prepared a solution of sodium hydroxide? Again, we don't need to know that number, but now it says they prepared a different solution of sodium hydroxide with twice the concentration. So now we have to consider how that would affect this curve. Are we titrating a different acid? No. Okay, so we're not going to have the pH of the original acid was around 2. We're not switching to a different acid, so we should start our curve right around that same spot. But now, because we are using a sodium hydroxide solution with twice the concentration, instead of finishing at 16, we're going to finish with half the amount of sodium hydroxide that we need. Why half? Because we have double the concentration, so it's going to be half the number of milliliters. Now, did my halfway point still go through around 4? I hope so, but I'll go ahead and take a look at the official scoring guidelines, and you can see that my quick sketch is what I came up with here. Let's take a look and see what it says on the official scoring guidelines. So yeah, what they were looking for would be showing that the drawn curve, the one that's solid, begins at the same pH, gradually increases, rising sharply at, again, not 16 milliliters, but 8 milliliters. And I think this was worth 2 points, that the location of the equivalence point at 8 milliliters will earn you 1 point, and then in general showing the rapid rise so that it follows that general shape of a titration curve. All right, well, this was a 10-point question, so we're not done yet, but so far this would be 1 point for circling the correct hydrogen, 1 point for the calculated molarity of sodium hydroxide, 1 point for the correct pKa, 1 point for the correct location of that X based on the particle diagram and justification. So that's 5. And then we have 6, 7. All right, there's 3 more points for part E. So we'll go ahead and take a look at the next part of this question. So we're done talking about acids and bases. What they try to do on a long question on the AP chemistry exam is they're not going to have it be all about equilibrium or acids and bases or kinetics or thermochemistry. It's a little bit of each. So we had some questions involving molarity, acids and bases, and now this is thermochemistry. In a third experiment, the student investigates the enthalpy of the reaction between lactic acid and sodium hydroxide. So it's about heat. It's about Q. So I'm going to see if I can write on my screen here. Just switching colors. Okay, so I'm going to write Q equals mc delta T. Calculate the quantity of heat produced in this reaction in units of joules. All right, well, the mass of the solution is 200 milliliters is actually a volume, but it says assume that the density of each solution is 1 gram per milliliter. So 200 milliliters, that would be 200 grams. Okay, so I'm going to write 200 for my mass. They give me the specific heat capacity in this problem. And now the change in temperature, it was 20 degrees Celsius. Now it is 23.2 degrees Celsius. That's a difference of 3.2. So if you do that math, you will get your answer in joules. You don't have to worry about a positive or a negative sign here because, in my opinion, quantity is kind of like magnitude or absolute value. But in the next part, include the sign in your answer. That's because it's going to be delta H. So we're going to take the heat. This is now an example of error carried forward. We're going to take the heat that we got in this first part, We're going to divide by 1,000 so we can get kilojoules, and then per mole. Now, you might not know how to figure out the moles, but this is going to be a chemical reaction in which the lactic acid is reacting with the sodium hydroxide. Do not, repeat, do not add the moles together. Okay, so if I have a certain number of moles of lactic acid, great. If I have a certain number of moles of sodium hydroxide, great. It's based on the limiting reactant. It's not based on the total number of moles. So just real quick math in my head, 0.1 liters times 0.5 moles per liter, I'm expecting that the number of moles of lactic acid is 0.05. But I'm not going to add those moles together. Let me go ahead and show you the official scoring guidelines here. Okay, so I'm going to scroll down and we can see the first part. So there is the M times the C times the delta T. So it's approximately 2,700 joules. I'm not worried about the sign here. But now they took that number of joules divided by 1,000, that would be 2.7 kilojoules, and they're slapping a negative sign on it. This is an exothermic reaction. And if you're thinking, well, how can you tell it was an exothermic reaction? It's because it got warmer. It was 20 degrees and now it's 23.2. So the entire reaction is releasing energy. It's exothermic. It's getting hotter. There's no hot plate. There's no Bunsen burner. This is not being heated. It's producing heat all by itself, which is why it got warmer all by itself. But then you can see the denominator is the number of moles. Not the combined number of moles, but the number of moles of either of those reactants or the limiting reactant. All right, and then the last part of this question. A student claims that if, for whatever reason, heat is lost from the calorimeter to the air, that the experimental value of the molar enthalpy will be smaller in magnitude. Well, if you're losing heat, I would think that you're going to have a smaller delta T. And if you're losing heat, then you're going to have a smaller delta T, a smaller calculated value of Q, and a smaller calculated value of delta H. So again, referring to the magnitude, so don't get confused about that negative sign, smaller magnitude. I would say yes, I agree with the student's claim because a smaller change in temperature because you're losing heat to the surroundings. So again, back on the scoring guidelines here. Agree. The heat lost from the system would result in a lower final temperature, which results in values of delta T being smaller and therefore Q and delta H being smaller. So now I'm not going to go to question 2 just yet. You've just seen the official answers and you could click on those scoring guidelines in the that Google document. What I want to do now is just remind you that this was something that I didn't actually put in the Google document specifically, separate links, but it's right here. So watch what happens when I click on this 2024 free response questions. There are the free response questions for 1 through 7. There are the official scoring guidelines, the Chief Reader Report, which gives lots of great examples of common mistakes that students make, so check that out. But then take a look at these sample responses. So I'm going to use sample responses for question 1. So these were on my computer. I'm going to go ahead and open up these. But you can find them on that website. They're linked. So when this document loads, what we're looking at now, besides the official scoring guidelines, are actual student answers. Okay, these are actual student answers, and you wondered, how did they do? How did these students do? Well, what they do typically on these sample responses is the first student you're going to see, they earned all points. So if it was a 10-point question, they got all 10. If it was a 4-point question, they got all 4. But then they give you 2 other student responses. So the first one is the one that earned all of the credit. So now I'm going to go to, again, this is one of the purposes of this session tonight, is talk about common mistakes that students make. Okay, here we go. This is the student who did not earn full credit. So I'm going to read you the commentary from that document. Okay, so I'm just going to make sure I got my pages lined up here. Okay. So here is the commentary for this particular student who did not earn full credit. They got 5 points out of 10. So as I'm scrolling through this document, you can kind of double check and see should they have earned the point or not. So the point in part A was earned for circling the correct hydrogen. The point in part B was earned because the correct molarity is calculated and they show their work. All right. 3.8, yes. The point was earned in part C for a correct pKa value, which is in the acceptable range, somewhere between 3.7 and 4. In part DI, they did put an X in the correct location. Let's see if they justified their answer. They said at the half equivalence point, those two things, lactic acid and the lactate ion or the conjugate base, should be equal. But because there is more molecules of the ion in the diagram, then pH is less than pKa. So they did earn the point for the justification. All right, moving on to part D triple I. All right, take a look at what they did with their curve. Doesn't look like they earned the point since they didn't make their curve have a titration stopping at the equivalence point, not at 16, but at 8. So as I'm reading the commentary, it says, the first point was not earned because the equivalence point is not at 8, and the second point was not earned because the curve starts at a different pH. So that was worth 2 points, and they lost both of those for different reasons. All right, did they get the right calculation for the Q equals MC delta T? In part EI, the point was not earned because the response uses 6.50 grams of sodium hydroxide instead of 200 grams of solution. So again, I'm just trying to show you some examples of common student mistakes. Then you can think about, as you're about to prepare for this exam day in the morning, watch out for situations like that. It's going to be not grams of the solute, but grams of the entire solution in this calorimetry experiment. All right, moving on. It says in part E double I, this could be potentially error carried forward. It says in part E double I, the point was not earned because they used 0.1 mole. They added the moles together. See how you can see that in the denominator there? They did not use 0.05, which is the moles of the limiting reactant, or one of the reactants. They combined them. And there is no negative sign. So this student could have earned error carried forward based on the mistake in part EI, but they made other mistakes in part E double I. All right, student claims about the whole heat is lost. They say, I disagree. So they do not earn the point in part E triple I because they incorrectly indicate that the magnitude of the molar enthalpy would be larger, not smaller. Okay, so you can see in examples like this, I just wanted to give you a sense that if you go back to the place where you can find these free response questions, the scoring guidelines, Chief Read Report, if you click on any one of these, it will take you to some sample responses, and there's commentary at the end. So if I go back to the document I was showing you with the student responses, I'm not going to go through both of these, but at the end of this document is a commentary telling you exactly what they earned. So you can see like student A earned all 10 points, student B earned 5 of 10. They kind of explain what they did right and what they missed. And then student C earned only 2 points, and you can kind of take a look at that. So again, that's one of the purposes of tonight's session, is to show you actual student responses, and hopefully you can take a look at some of those mistakes that students made. So I'm going to go ahead and close some of these documents right now. I'm going to go back to the next FRQ. Okay, so this is of that same year. This is question 2. Looks like we are talking about something involving an acid, but this is not necessarily an acid-base reaction. They wouldn't give you 2 acid-base reactions with, titration curves in the same question. So this is more about perhaps stoichiometry or limiting reactants, something else. We'll take a look. Part A, calculate the number of grams of CO2 produced. We're just literally going from moles to grams. So I'm going to go ahead and write down the number. Okay, so the number here is 0.0114 moles of CO2. And if I do that math, it's approximately 44. 12.01 for carbon, 16 times 2 for oxygen. So sometimes on the AP chemistry exam, you might be asking yourself, is it really that easy? Oftentimes, the very first part of a question, the very first part of a free response question is intended to be very accessible. So you might think, how can it be that easy? They don't want to scare you off with, some fancy buffer or equilibrium or kinetics question in the very first part. So oftentimes the easiest question or the most accessible question that doesn't require a lot of challenging, complicated problem solving is the very first part, part A. So if I go ahead and open up the scoring guidelines, all right, let me go ahead and, again, these are the scoring guidelines for the 2024 exam. I'm going to move down to part B of this question. I'm sorry, not part B, question 2, excuse me. There it is, just literally going from moles to grams. Okay, so that was straightforward. Again, you have access to these scoring guidelines, so you might be thinking, I already know what these answers are, but I'm just kind of walking you through the strategy of like what's going on in my mind when I'm thinking about how to set these problems up and so forth. Okay, so the next part is that the CO2 that was produced from the reaction, now we are given a temperature, we are given a pressure, and the number of moles has already been given to you as well. So we have moles, we have temperature, and we have pressure. So we're going to go ahead and use, I'm just going to switch color. I don't really want to do in red every single time, so let me switch. All right, so we're going to calculate using the ideal gas law. Now, because the pressure is in atmospheres, we're going to use 0.08206, which has units of liters, atmospheres, per mole, per Kelvin. So we definitely have to change this temperature into 293 Kelvin. We are solving for volume, so it's going to be V equals nRT over P. So I'm going to take the moles from the previous part, which is 0.0114, times the gas constant from the equation sheet, times the Kelvin temperature, divided by the pressure, and that will be my volume in liters. So if I take a look at the scoring guidelines, there it is. There's the setup for V equals nRT over P. Okay, next part. The student performs a second experiment that is identical to the first, except that the student grinds these chunks of solid into a powder. What happens to the surface area of the reactants when the student grinds these larger chunks into a powder? The surface area increases. The surface area increases. So think about the fact that if it was a cube or large, chunks, then there's only so much surface area exposed to the liquid. But the fact that it's ground up into a powder, there's tiny particles, increasing the surface area is all they wanted. And then it said, would the rate or the time required for dissolving of the solids longer, shorter, or the same? So it's actually about the time. The rate would increase, but it's going to be a shorter time. And they say, justify your answer based on the collisions. That's a really important point. When they say, justify your answer based on, that could be Coulomb's law or atomic principles or the strength of the intermolecular forces or the collisions, then that's what they're looking for. So we've already said that the surface area is going to increase. It's going to be faster, but they wanted time, so shorter time, and then increasing the number of collisions between the particles. Okay, so here's what it said on the scoring guidelines. Surface area increases. Time shorter than, because the larger surface area increases the number of collisions. So faster rate of dissolution, more frequent collisions between the water and the surface particles. There's that. All right, next part. When the reaction is complete, will the volume of CO2 at the end of the second experiment be greater than, less than, or equal to? Don't forget, in a question like this, If you just justify your answer and you realize, oh, read that question that you just, or the answer that you just wrote, read it one more time. I did all this justification, but I forgot to say the words greater than or less than or equal to. So make sure that you are answering the question and then giving your justification. And this is not a, I'll just flip a coin and hope I get lucky. Most likely this is a 1-point question, so you don't get a point for just simply guessing. It's going to be correct answer with the correct justification. Now, if I look at the details, the student performs a second experiment that is identical to the first. We're not adding more, we're not adding less in terms of the number of moles. So I would say same amount of CO2, same volume of CO2. Just because it's going to happen faster doesn't mean you're going to produce more CO2. So I'll show you the scoring guidelines on that one. Equal to. Again, you get 1 point for a correct answer and a valid justification. Because we have the same amount of reactants in terms of number of moles, it's going to produce the same number of moles of CO2. Okay, so far we've seen 1 point for a very easy moles to grams, 1 point for using the ideal gas law, 1 point for saying surface area increases, 1 point for saying shorter than and talking about the collisions, 1 point for saying equal to because same number of moles. All right, so a few more points left on this. We're trying to get to a total of 10. So we got a few more points to take a look at. All right, next part of this question. The student conducts additional trials of the experiment and produces the following data table. All right, so now what I'm going to do is a traditional limiting reactant calculation, and then I will show you that there is a way you could have done this without doing any math at all. Okay, so here's the traditional limiting reactant calculation. 1.543 grams of this chemical. So I could convert that into moles. And then I could do the same with the other one, 1.251 grams of NaHCO3. I could convert that into moles. And if I look at the balanced equation, I got to go back to the beginning here. What's the balanced equation? All right, so there's 1 mole of this chemical for every 2 moles of that. So I could look at the number of moles and I could decide, do I have exactly twice as much? If I have a perfect 1-to-2 ratio, I think that would not involve a limiting reactant. But if there's like more than 2 moles of the NaHCO3 compared to the moles of the other chemical, then I would say there's an excess amount of baking soda, the sodium bicarbonate NaHCO3. So I'm going to see if I could find an easier way than doing all of those calculations. What happened from trial 3 to trial 4 is they increased the amount of NaHCO3, but they didn't change the amount of that. Now, had this been, I'll just say excess with a question mark, okay? Had this been excess, then there'd be no difference in the amount of product produced. But what happened is the amount of product actually increased. So therefore, this is not excess. This is my limiting reactant. I can tell it's my limiting reactant because when its concentration or amount was changed, it did increase the amount of CO2 produced. So when you look at the scoring guidelines, there's a variety of ways of proving the limiting reactant, but that would be a very efficient way of determining that the limiting reactant is going to affect the amount of product. So if you increase the amount of the limiting reactant, it will affect the amount of product that's produced. If you increase the amount of the excess reactant, it's not going to make a difference. So anyway, let's go ahead and take a look at the scoring guidelines. You're going to see multiple ways on the scoring guidelines to verify. Okay, so sodium bicarbonate, or NaHCO3, is the limiting reactant because changing the mass of that substance alters the amount of CO2 produced. Or you could go ahead and convert each of them into product and say that the limiting reactant was the one that produced the smaller amount of product. So 2 ways to do it. One more traditional with respect to grams and moles, but the other just kind of paying attention to how those variables were changed. All right, now we have to talk about entropy. So back to this. This is a Unit 9 topic. The reaction has a value of delta S, so the change in entropy, that is greater than 0. That means that entropy is increasing. Using particle level reasoning, explain why the entropy increases. Okay, let me go ahead and erase things on this slide if I can do that. Let's see if it will let me do that. Oh, no, because I already saved it. Let me do it like this. I'm going to just manually get rid of my drawing here just so I can focus on this. Okay, so you can just kind of see I've got 1 mole of the first reactant, which is aqueous. I've got 2 more moles of the second reactant, which is aqueous. So the chemical that I'm really focusing on the right side of the equation that would justify an increase in entropy is the CO2. Why? Because it's not aqueous, it's not a liquid, it's a gas. That's a pretty huge increase in the number of microstates, or you could say greater number of possible arrangements. But if all you do is you say that there's gas on the right, not on the left, you never talked about the particle level reasoning. So it's got to be something specific about the CO2 gas molecules have a greater number of possible arrangements or a greater number of microstates, but not just mentioning the phase, but talking about the particle. So again, justify your answer based on collisions. Here it says using particle level reasoning. They're giving you a clue. That's what they want. Now the last part. Oh no, we actually have 2 more. All right, part E says the student notices that the temperature of the reaction mixture decreases as the reaction takes place. Now, in the previous problem, so question 1, it actually got hotter, and that was an exothermic process. This one's getting colder over time. So student notices that the temperature of the mixture decreases. So this is endothermic. They're telling you it's endothermic. The student claims that the reaction is favorable at all temperatures. Okay, let's go ahead and talk about delta G here. All right, so delta G equals delta H, which we were just told was, well, it didn't actually tell us that delta H was positive. They said endothermic, so we have to know that. They told us it was endothermic, but we had to know that delta H was positive. All right, minus T delta S. Again, they're telling us that delta S is positive. Is this favored at all temperatures? No. This is one of those, it depends. Okay, if it were favored at all temperatures, the delta H would have to be negative, and the delta S would have to be positive. That would be favored at all temperatures because delta G would be negative no matter what. This is only going to be favored at high temperatures. So do you agree or disagree with the student's claim? I would say I disagree with the student's claim, and I'll have to talk specifically about delta G, and the sign should be negative, but the sign of delta G would be negative only at high temperatures because delta H is positive, and that would not obviously cause delta G to be negative. So I'll go ahead and show you the scoring guidelines for both D and E. Okay, so there's that particle level reasoning. The entropy change is positive because the aqueous reactants produce 2 moles of gas particles. Gases are far more dispersed. Keep going. Got to talk about the particles. So they said greater number of microstates. They also could have said the gas particles have a greater number of possible arrangements, but definitely talk about the particles and not just the word gas or the word dispersed. Okay, so microstates is a particle level reasoning, but so is the gas particles have a greater number of possible arrangements. So that was the part about why is the entropy positive. And then here comes the, I disagree with the student's claim. The reaction is endothermic and has a positive entropy change, so it's only favorable at a high enough temperature such that the magnitude of the negative T delta S is greater than the magnitude of delta H. Or you could say something about delta G is negative, but again, if that were true, then the reaction would have to be exothermic. It's like kind of saying, like, if that claim were true, you would need the delta H to be negative, but in this case, delta H is actually positive. All right, last part, F and G, looks like we are going to do a little more acid-base chemistry. Now, you have 2 different Ka values. And so what they want is the pKa2. So we're not adding these two equations together. We're not combining the equations together. We're just going to focus on the negative log of the pKa for part 2 or reaction 2. So the negative log of that would be approximately 6 point something if I did that math on my calculator. So if you do that math, the negative log of that number is around 6.07. And then last part is related to buffer solution. A buffer solution with a pH of 7 is prepared using these two chemicals, and they want the ratio. So if I were to write pH equals pKa plus the log of A minus over HI. Again, this is the Henderson-Hasselbalch equation from the equation sheet. So there's our ratio right there. And so a buffer with a pH of 7. So pH of 7. I can plug in the pKa that I have calculated, and then I can solve for the ratio from that log. So I'll go ahead and show you what the scoring guidelines look like for that part. You can see how they set it up. So pH equals pKa, just of the reaction 2, not the whole thing. We're not adding them together. So pH equals pKa2 plus the log. So they did the math of 7 minus 6.07, which was the pKa2. So 7 minus 6.07, and then they did 10 to the minus that value, and they got a ratio of 8.5. Again, there's the official scoring guidelines. Now what I want to show you, of course, is the what did a student do wrong? So here comes mistakes that were made on this question. Okay, so what you're looking at right now would be the first answer is going to be the best answer. All right, let me get my commentary for this particular question. All right, so first answer is going to be the full credit. All right, so that student earned all of the points, but I'm going to get to the student that didn't get a full credit so I can focus on mistakes that they made, and that's going to be right about here. Okay, so this student earned 4 out of 10 points. So I'm going to just read the commentary as we're taking a look at these student responses. Let's see how they did with converting moles into grams. All right, so again, that student got 4 out of 10 points. In part A, the point was earned for a correct calculation using the molar mass of CO2. Let's see how they did. Looks like they did convert Celsius to Kelvin, so that's good. Use the ideal gas law constant. The point was also earned in part A II for a correct calculated volume of CO2. Surface area increases. Yes, the student earned the point in BI for a correct claim about surface area, but the point was not earned in part BII for an incorrect claim about reaction time. So they said the time would be greater. Maybe what they meant to say was the rate would be greater, and maybe they just didn't pay attention to that word. If they meant to say it's going to be a faster rate, but instead they said the time would be greater, that might be that they understood the chemistry but didn't quite pay attention to the language and the word choice. So, yeah, that's unfortunate. All right, next part. The volume of CO2 in the second experiment will be, they said less than. No, it's going to be the same because it's the same number of moles and same amount of reactant. So they didn't earn the point in part B III. Didn't really quite get the whole limiting reactant, didn't really justify their answer part. So it says in part C, a point was not earned because although sodium bicarbonate, NaHCO3, is correctly identified as the limiting reactant, there is no justification to support the claim. So just pay attention to that. You're not going to get credit for just a choice or a coin flip. You have to actually justify your answer. All right, let's see if they had particle level reasoning in part D. Entropy, which is a measure of the disorder. All right, keep going. Talk about particles. Increases because there is an increase in volume and temperature. No, they did not use particle level reasoning, talking about the gas particles and their relation to the dispersal of the particles or the microstates. So, no. All right, I agree with the student's claim. In order for delta S to be positive, delta G must be negative. So no, they didn't talk about the delta H, so they did not earn the point in part E. Yeah, incorrect claim about the conditions of thermodynamic favorability. All right, part F. Yes, there's the 6.07. Looks good, but no, they did not quite do a calculation or explain what was going on in terms of that ratio. They said they must be equal since the solution has a neutral pH of 7. So the student is confusing a pH of 7 with a strong acid and a strong base. This is a weak acid and its conjugate base. So this would be a Henderson-Hasselbalch calculation, but that student assumed that a pH of 7, that these two components would be equal, but that's only true for things like strong acids and strong bases like H plus and OH minus. Okay, so I'm hoping that this is a helpful process where I'm trying to talk about the correct answers and then show you some sample student mistakes to kind of guide you. So I'm going to go ahead and go back to our next question in the 2024 AP Chemistry for Response questions. Actually, let me just pause for a moment. I don't know if it's going to be helpful. Yeah, see, I'm not paying attention to the chat, as you can tell at all, because I'm sharing my screen. So again, I apologize if you're asking all kinds of great questions, but my chat is not something that I can easily monitor when I'm taking a look at sharing my screen. So anyway, what I will do, clearly, if I'm missing things that you are talking about, I will try to look at the comments and then respond to you after this review session is over. So anyway, just it's hard to kind of monitor live chat and also do all of these screen shares. Okay, now this is question 3. Sterling silver is an alloy, and the first question that they're going to ask us, again, very accessible in a 10-point question, is just oxidation numbers. Now, I say it's accessible. If you don't know how to assign oxidation numbers, this might not be easy, but they're intending the opening question to be not requiring a whole lot of heavy lifting or conceptual things. So like circle a hydrogen atom, that was easy. Convert moles into grams, that was easy. And then hopefully assigning oxidation numbers would be easy. So it's going to be 0 for an element, and it's going to be positive something for the silver as a metallic ion. So if you don't know the charge on silver because of the periodic table, that's okay. Charge on sulfur should be -2 based on its location, and we have 2 silvers for every 1 sulfur. So we're looking for 0 and +1. Let me go back to my scoring guidelines. Let's see, I'm going to close this document and keep this one open. All right, scoring guidelines say that the oxidation number of silver should be 0 and +1. All right, next part. We're not predicting whether this is a substitutional alloy or an interstitial alloy. Because you know what? I don't know for sure if 145 is close enough to 165 or if 145 is smaller than 165 and could fit in between the spaces. Doesn't matter. I don't have to make that choice. They're telling us it is better classified as a substitutional. So don't disagree with the question stem. You know, if you look at this and you say, it's wrong or you're wrong, this is not a student claim. They're telling you it is better justified or classified as a substitutional. So if your argument is, I think it should be interstitial, you can't fool me, College Board. No, this is intended to be a justification that's based on what they told you. So it looks like 165 and 145 must be close enough because they're telling us it is substitutional, and therefore the atomic radii are comparable in size. So on the scoring guidelines, silver and copper have similar radii, so that's why it would be substitutional and not interstitial. Okay, next part. Again, kind of like with the justify your answer in terms of collisions or justify your answer in terms of particulate level understanding, using principles of atomic structure and Coulomb's law. Explain why silver has a larger atomic radius than copper does. Now, if this is your argument, okay, so here's copper on the periodic table, Here's silver underneath it. If your argument is, well, size gets bigger as you go down, that's not using principles of atomic structure. So let me just erase my drawing here. Okay. So I'm thinking that maybe it would be a good idea to look at where these are on the periodic table, but also look at their electron configurations. So let's see. Copper would be 29 electrons. And then I think silver is going to be 47 electrons. So we're talking about 4s2 3d. Actually, copper happens to be an exception to the traditional electron configuration, but it doesn't matter. It's actually 4s1 3d10. That doesn't matter. It's 4s and 3d. We'll just kind of leave it at that. But when I get down to silver, it's going to be an entire, it's going to be an entire other level. So silver would be, let's see, can I erase? Let me get to my erasing tool here. There we go. Yeah, I just have to jump to the next noble gas. Let me go back to my pen. All right, so the noble gas below argon is krypton. So Kr. And that would be 5s and 4d. So greater number of occupied energy levels. Not just more electrons, and not just size gets bigger as you go down. Don't talk about protons, because that's not going to help you. Greater number of occupied energy levels. Not just more shells. Greater number of occupied energy levels. That would be the best way to say that. Let's go ahead and take a look at the official scoring guidelines. Silver has more occupied electron shells. They're talking about level 5 versus level 4. And then again, they did talk about Coulomb's law, so it's going to be weaker Coulombic attraction. Electrons are farther away from the nucleus. All right, let's go back to our next question. Again, you've got these scoring guidelines. I'm not going to read them necessarily and just say, here it is, but I'm just trying to call your attention to maybe some mistakes that students will make, and they might just say more electrons, or size gets bigger as you go down, but definitely talk about the electron configuration, greater number of occupied electron shells or energy levels. All right, so they had mentioned something about a sterling silver alloy. Let's go ahead and revisit that. Here comes a chemical reaction. So there's tarnish, which has the chemical formula Ag2S, and it can be removed until you get just sterling silver. So they're getting rid of this tarnish. So the student weighs the tarnished sample, and then they remove it, and then they weigh the clean sample. So that difference in mass would represent the number of grams of Ag2S. Okay, so we subtract, we get that difference, and then we can convert from grams to moles. But now, here's an important point that sometimes we know what we think the question is asking, and then we don't read all the way. So some students would stop right about here. And they kind of just ignored this part. So they were very successful at subtracting those two numbers. They were very successful at going from grams to moles, but they thought that they wanted the moles of Ag2S. So close. No, they actually wanted the number of moles of silver, as in Ag, and so they forgot to multiply by 2. Okay, so I'm going to show you the official scoring guidelines here, and you can see that times 2 was probably a very common thing for students to not do at the end. Right there. Okay, difference in mass. Use the periodic table, go from grams to moles, but again, read the question carefully. They wanted moles of silver, and I think because if you got this far and you got the right number of grams, you got 1 out of 2 points, but I'm thinking that students that made that mistake would only earn 1 out of 2 points for that one. Okay, next part. I think we're going to do some electrochemistry here. It says rhodium plating, and you're like, wait, aren't we just talking about silver? Well, rhodium plating is a process used to protect sterling silver from tarnishing. Now, we do have 2 half reactions. Is this a galvanic cell or is this an electrolytic cell? Well, the clue that this happens to be an electrolytic cell is because of the word electroplating. So electroplating, okay, so rhodium plating, okay, that is referring to a process that requires electricity. So electroplating. Another clue is it says oxygen gas is produced, which means that this reaction must be reversed. Okay, so why is that reaction going to be reversed? Because you need oxygen gas to show up as a product, and right now it isn't. And if you're worried about, again, thinking about a galvanic cell, it's okay that when we add these two half cell potentials together, it's okay that it's negative. That's not going to be a problem. A negative cell potential is referring to a thermodynamically unfavored process, which is why you need a battery to make this happen. So a clue is that solid rhodium is formed on the surface of the metal. So they also mentioned that, okay? So rhodium is formed, so that this one we're not going to flip. We're just going to go ahead and leave this as is. So because rhodium solid is being produced, oxygen gas is produced, we have to flip that one, and it's okay for this to be a negative cell potential. So delta G is positive, which means this is not thermodynamically favored. Cell potential is negative, which means, again, this is not thermodynamically favored. So here's the answer for that balanced equation. You do have to get the electrons to cancel out. So we're going to multiply one of them by 4, and we're going to multiply another one by 3. So I'll show you the answer. They multiplied one of these half reactions by 4. They multiplied another of these half reactions by 3. They added them together. So that was the balanced equation. And again, look at that negative 0.43. One more thing to mention. I'll go ahead and go back to the PowerPoint, talk about this. Okay. So when we multiply, this is going to get multiplied by 4. We do not, repeat, we do not multiply the cell potential by 4. The only thing you ever do to a half reaction's cell potential is change the sign when you reverse it. Do not multiply by 2 or by 3, okay? This one is going to get reversed and multiplied by 3, okay? So here are the two modified reactions, okay? So there's my coefficients. I'm not having to put states of matter in my answer on the AP chemistry exam, so I'm choosing not to do things like A, Q, and S. That's not required when you're writing a balanced net ionic equation, but there's my coefficients of 4, 12, and 4. And then I'll go ahead and change color. Okay, so the other one that I flipped and multiplied by 3, it's going to be 6 water, because I multiplied by 3. And it's going to be 3 O2, 12 H plus, and 12 electrons. Do not put electrons on both sides of the equation, kind of like spectator ions. If you have 2 sodium ions on the left and 2 sodium ions on the right, don't put that in your final answer. So we're going to cross off the electrons and then just write our final answer. Okay, so I'll have 4 moles of rhodium ions on the left and 6 moles of water on the left. And on the right, I have 4 moles of solid rhodium, 3 moles of oxygen gas, and 12 H pluses. But again, you don't need to put phases of matter. So again, there was that answer to that particular question. And there's the cell potential, which again, it's 0.8 because we didn't flip it. We multiplied by 4, but we don't change the magnitude of the cell potential when you multiply the coefficients by 2 or 3 or 4. But then the one that we flipped, then we changed the sign for that one. So that's why that was positive 0.8 plus a negative 1.3. Now, the next part is related to the fact that this is not thermodynamically favored. So we have our cell potential, and it says, based on your answer to part DII, which was a negative cell potential, explain why this process requires the use of an external power source. Wow, what a big hint they just gave you. If you got a positive value for this part of the question, you should already realize something is up. because how can I have a positive cell potential like for a galvanic cell, which is normally is thermodynamically favored? Why would it require the use of an external power source? So it's kind of hard to do error carried forward. If you got a positive cell potential and then you justified why it needs a external power source, it's not really consistent with that. So that might be your clue that maybe I should make sure that that cell potential is negative since it's not thermodynamically favored and requires an external power source. All right, now we'll go ahead and do this one. So 2.8 grams of rhodium. So first I can go from grams of rhodium to moles of rhodium. Now, if you're not sure what comes next, well, it says they want the length of time in seconds, and amps are also known as coulombs per second. So our final answer is probably going to look like seconds, which means our final conversion factor is probably this. So before I can go from moles of rhodium to coulombs, I have to go from moles of rhodium to moles of electrons. And again, that comes from that half reaction, whether you multiplied by 4 or not. There's a 3-to-1 ratio in terms of electrons. Okay, so there's 3 moles of electrons for every 1 mole of rhodium. Now here comes the 96,485 coulombs for every 1 mole of electrons. And no, this is not a constant named after me. So anyway, we've got 2.8 grams of rhodium. Use the periodic table to go from grams to moles. Then look at the half reaction and get that ratio of moles of electrons to moles of rhodium. Then use the Faraday constant, 96,485 coulombs per mole of electrons. And then finally, you get, ooh, I didn't do it correctly. Whoops, I was going too fast. Sorry. Yeah, this needs to be upside down. Sorry, we need to put coulombs on top and 1 mole of electrons on the bottom. See, look at that. If you're on the AP exam and you realize, wait, how can I get coulombs on the bottom? I need to flip that upside down. That would be a time to just scratch it out or erase it and do it over again. All right, so grams to moles of rhodium to moles of electrons. Then from moles of electrons to coulombs, and then finally from coulombs to seconds. So here is the setup from the official scoring guidelines. This was worth 2 points, okay? Again, 1 point for getting to moles of electrons and then 1 point for time. Now, you didn't have to do this in 2 separate steps, but they gave you credit for like the first 2 conversion factors. But then assuming you might have messed up something else, you're going to get, 1 of possibly 2 points if you made 1 mistake in your conversion factors. All right, now we are coming to the student mistakes. Let me go ahead and find my script for question 3. I'm going to pull up, and again, you can find these on the College Board site. Okay, sample responses, you can find them. These are just already downloaded to my computer. So this is, we start with the student who got all 10 points, and then we're going to take a look at mistakes that were made. And again, I'm trying to call your attention to a student made this mistake, so learn from it and don't do it. All right, so again, first student earned everything. So let's go ahead and skip past that. All right, here we go. This student earned 6 out of 10 points. The point for part A was earned for correctly indicating the oxidation numbers. The point in part BI was not earned. The response classifies sterling silver as an interstitial alloy without justification. So they said it consists of silver and another element, as if it's just like a mixture versus a pure substance. So it didn't talk about the comparable atomic radii. All right, let's see if they earned the point in part part BII. According to atomic structure, okay, let's see what they said. Atomic radius of silver is greater than copper. All right, keep going. Because silver is 1 group lower than copper. Extra electron shell, that seems pretty good. So yeah, In part B, double I, they got the point for talking about an extra electron shell that was occupied. They didn't just say size gets bigger as you go down or that there's more electrons. So that was a good use of principles of atomic structure. Okay. Difference in mass, yes. Converted grams to moles, didn't read carefully. Did they actually go all the way to moles of silver? No. So my commentary for part C says, the first point was earned for correctly determining the mass of Ag2S, but the second point was not earned because the stoichiometric ratio is not applied to calculate the moles of Ag. Okay, now on to part D, double I. Ooh, I kind of like the rhodium multiplied by 4, but what the heck? Oxygen is on the left. It tells you that oxygen gas is produced. So it looks like they did not flip either of those equations. No, actually, they flipped the wrong one. They flipped because I see solid rhodium is actually on the left and it's supposed to be on the right. And yeah, look at that cell potential. Is it negative the way it should be? No. Can they justify why an external power source is needed? I don't think so. So I'll just read you the commentary for part D. Part DI did not earn a point because the balanced equation is reversed. However, part D double I did earn the point for the error carried forward. So they did make a mistake in part DI, and they got the error carried forward in part D double I, which, hey, great. Thank you, College Board, for giving me some partial credit. But I don't know what they're going to say in the next part. Let's find out. See, they think it's a galvanic cell. So part D triple I, the point was not earned for incorrectly stating that a galvanic cell requires an external power source. That should have been the clue that that student should have realized, wait, I think I did this backwards. Because if you require an external power source, then you are not thermodynamically favored, and you would have a negative value for your cell potential, your voltage. Looks like they did get both points in part E. They went from grams to moles of rhodium, from moles of rhodium to moles of electrons, from moles of electrons to coulombs with the Faraday constant, and then finally to time. They got around 3,900 seconds. Okay, so again, you can see they got 6 out of 10 points. All right, moving on to part 4, question 4 of the 2024. Okay, this is question 4. This is not a burette. It's a thermometer, but you need to know how to read it. So burettes, you read them from top to bottom. This one is a thermometer. You're reading it from bottom to top. Is it 30? No. Is it 35? No. It looks like it's 36, 37, somewhere between 38 and 39, and you need to show the correct number of decimal places. So if this was a burette, that would be different. Okay, if this was a burette, you'd have a different kind of arrangement here, but I would say it's somewhere between 38 and 39. Another difference in a burette is that every hashtag or every little hash mark on a burette is a tenth of a milliliter. So a burette is actually read out to the 100th place. This should be read out to the 10th place. So 38.5, they probably accept a little bit of a range, but it looks like it's about halfway between 38 and 39. Anyone that said 39 would not earn the point. If you said 38.50, that would not earn the point. So what they're looking for is specific number of decimal places based on the precision of that piece of measuring device. So 38.5 is what they wanted for that answer. And then now we have to understand what's going on in terms of if it's getting hotter, and I think it is, because this hot metal cube was added to water. So we had a piece of metal in boiling water. It was 100 degrees Celsius, and then it was added to room temperature water. So the metal cooled down, the water warmed up. And so if the water warmed up, we need to show arrows going a little bit faster. Now, why isn't every single arrow the same length? Well, not every particle is traveling at the same speed, but on average, you need to draw arrows that are longer to show that they are hotter and faster. So correct answer for that next part was the after drawing should contain arrows that are longer on average. Looks like we have another Q equals mc delta T. And this time, we're not calculating the heat. We are calculating the specific heat. So that's like the C in this calculation. So not the Q, but the C. Okay, so what's our C? Well, our C is unknown. What's our M? We'll go back and figure that out. What's our delta T? We'll go back and figure that out. But it's 2,940 joules equals M times C times delta T. But this is the thing that we don't know. All right, so what's the M of the water? 52 grams. Now you might think, do we have to add them together? No, this is not a solution. Okay, this was not a solid dissolved in water. Those you would add together for sure. This is simply a hot piece of metal was added to a room temperature sample of water. So we're not going to combine the two masses together like you would normally do in a dissolving a solid in water experiment, because now the entire solution would be getting hotter or colder. This is transfer of energy from a hot piece of metal to a sample of water. So the mass is not going to get added together the way you would normally do with the solute and the solvent. It's just the water getting hotter. So 52. Okay. The C is, I don't know. And then the delta T for the water is 25 to the highest temperature that we recorded, which was like 38.5. So it's 38.5 minus 25. Now, I am not a big believer in final minus initial, because if I do Q, I never worry about sign. Okay, so I don't do like final minus initial. I just do the magnitude. So the magnitude is the change in temperature. It looks like it's going to be around 13.5 degrees, if I can do some mental math there. So there's my delta T. I don't care about whether it's positive or negative. I just care about the magnitude. My C is I don't know. So I pick up my calculator. I do 2,940 divided by 52 and then divided by 13.5. All right, let's take a look. Official scoring guidelines are, well, there's the 2,940 divided by, oh, oops. Yes, I was thinking of the water. I wasn't paying attention. I wasn't focusing on which substance was actually getting hotter or colder. So they don't want the specific heat of the water. Duh. They want the specific heat of the metal. So yeah, I was going a little bit too fast on that one, so I apologize. If I had read carefully, see, there you go. I'm modeling what you should not do on the AP exam. Is that I was thinking we're going to take care of the water and look at its specific heat, but no, this was the specific heat of the metal. So my bad on that one. Yeah, calculate the specific heat of the metal. Maybe you should read carefully next time. So correct answer was not focusing on the water. Correct answer was focusing on the metal. So there you go. Maybe you don't earn every single point on the AP exam if you don't read carefully like I just did. But anyway, there's my message to you. Read carefully. It was about the mass of the metal and the change in temperature for the metal. All right, now, next part, I think, has to do with an experimental mistake of some kind. In a second experiment, they switched from the metal that we were just using to aluminum. And they're saying, explain how the magnitude of the temperature change of aluminum compares with the magnitude of the temperature change of the metal. Now, if we did part C correctly, so you can kind of, let me go ahead and erase all of that. Okay, I'll show you the correct answer back again. Okay, so the correct answer was 0.47 joules per gram degree Celsius. Mass of metal is on the bottom. Delta T for the metal, that would be 100 minus 38.5. I'm not worried about T final minus T initial. So again, there's that. So 2,940, just pull up my calculator here. 2,940 divided by the mass of the metal, and then divided by the delta T, which is 100 minus 38.5. Okay, so that specific heat capacity of the metal is 0.487. Now, in the next experiment, we had 98.1 grams of the metal. We're still using 98.1 grams. We're just using a different metal. They're not changing a whole bunch of variables here. 2940 is not changing. 98.1 is not changing. So what is changing is the identity of the metal. It has a different specific heat capacity. So if I go back to my calculator, I would do 2940 divided by 98.1. Now I'm going to divide by a different value of C. This is a bigger value of C. So I'm going to divide by 0.897. Now look at my delta T. It's actually 33.4. Okay, so 33.4. How does that compare with the delta T from the previous experiment? Well, it was not 33.4. It was, in the previous experiment, it was like 61.5. So look at that inverse relationship. And what do I mean when I say inverse relationship? Okay, so if you have Q equals mc delta T, this didn't change in the two experiments. This didn't change in the two experiments. So here is the inverse relationship. If you use a larger value for the specific heat capacity, then this will be smaller. And that's what we can do mathematically or just talk about it conceptually. So explain how the magnitude of the temperature change of aluminum with a larger value of C would be different in terms of the, comparing the two experiments. I would say it's going to be a smaller delta T. I'll show you my scoring guidelines on that one. Again, you could do it mathematically or just talk about it conceptually. So here's one of the possible answers. The value of delta T will be smaller because aluminum has a greater specific heat capacity. Therefore, they're kind of talking about smaller change in temperature because it's a larger specific heat capacity. Or mathematically, you could go ahead and run the numbers and show that 33.4 is different than or less than 61.5. So there's that. Now, this was a 4-point question, which means we can go straight to the student who maybe didn't get all 4 points. I'm going to go read you my commentary for this. Okay, so let's take a look at the first potential mistake that the student could have made. Okay, so remember, this student got all 4 points. I'm going to read you my commentary for the one that maybe lost some points. Okay, these all look great, looks great, looks great, looks great. Okay, here comes the student that didn't get a full 4 points. Okay, this response earned 3 points. Well, I can see what they did wrong. It's right there. In part A, the point was not earned for recording an incorrect temperature from the thermometer. Looks like longer arrows, they got that point. Did their correct calculation, unlike what I was doing earlier. My apologies for not paying attention. Anyway, they got the correct value for the specific heat capacity of the metal. And the magnitude of temperature change of aluminum is less than that of the original. But just saying that would not earn the point. They have to actually justify because it has a greater heat capacity, meaning it requires more heat, and therefore they're saying a smaller delta T looks good. So they earned 3 out of 4 points. I'm going to go ahead and keep going because this is a short question. So close. It's not 38, it's 38.5. Now this person got only 1 out of 4 points. The point was not earned in part A because the temperature is not recorded to the correct number of decimal places. In part B, the point was earned for drawing longer arrows. So that was the only point that they got. Let's see what they did wrong here. I don't see the delta T. I see heat divided by mass. So nope. And then in part D, aluminum reacts differently. to the mystery metal provided. Yeah, they're not specifically connecting the temperature change to the specific heat capacity. So there you go. All right, well, if you're still hanging in there, we are going to continue. Okay, that was question 4. Let's move on to question 5 from the 2024 AP Chemistry exam. Hope you're finding this helpful. Again, the common mistakes, I'm just trying to call your attention to them. Or maybe even make some mistakes myself. Okay, this is question 5. Remember, hard brackets for Kc, and then use the capital P for Kp. So this is really important. I'm going to talk about this for just a second because this might come up in, future questions. All right, so there I'm doing concentration of Hi squared over concentration of hydrogen. Okay, now if they asked you to write the Kp for some reason, this is not enough. Some students think, I'll just change my hard brackets to parentheses. No, 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 no. Okay, so let me go ahead and switch to my eraser so I can get rid of all this. Okay, if they want a Kp, pressure of Hi squared divided by the pressure of hydrogen and then also the pressure of iodine. Okay, they didn't want a Kp in this question, but if they did, that is a very important distinction between Kc and Kp. All right, let me go ahead and erase my... Okay, so you know what a Kc looks like. Now, on to the next part. At a certain time, the value of the reaction quotient is 0.67. Okay, so that would be Q equals, and we have Hi squared over H and I. This is a random mixture. It's not the equilibrium system. It's just simply random point in time. So Q is like where we are at a point in time. If you're wondering, why are there 3 molecules of hydrogen and only 2 molecules of iodine? It can be whatever. They didn't say it started with only Hi or only an equimolar mixture. So I've just got some numbers. I'm going to go ahead and stick in the numbers into the appropriate spot. So draw the number of Hi molecules that are needed. So I haven't done that yet, but we are going to go ahead and put in 3 and 2. So 3 particles of hydrogen, 2 particles of iodine. And this is equal to 0.67. Now, 0.67 is approximately 2/3. So, you might be very tempted to put in 4 particles of Hi because you think, well, 4 over 6 is the same as 2 over 3, but that was a number squared. So the number that I'm looking for is 2. So I'm going to draw 2 particles of Hi because 2 squared divided by the product of 3 times 2 is equal to 0.67. All right, let me show you scoring guidelines for that part. Okay. So there's the expression with the hard brackets, the Kc, not a Kp, Kc. And it says additional 2 Hi particles were drawn. There you go. All right, next part. A student monitors the number of moles of Hi over time. So that's the y-axis. And then at some point where the time occurred, hypothesize an experimental change that could have been applied to the system. Now, it looks like Hi increased, but it says, assume that the student did not add more Hi. So read the question carefully. If they say assume that the student did not, then you can't say, I think the student added more Hi. Clearly, no. So if we look at our expression here, we have, it's going to be Hi. Let me just double check. Yeah. Okay. It's going to be Hi on the right. It's going to be H2 plus I2. Okay. Now, could we have changed the size of the container? like make it smaller or larger. No, that would not cause a shift at all because we have equal number of moles of gas on the left as on the right. So this is not one of those situations. This is not one of those equilibrium systems where it could be affected by changing the volume of the container. It is not going to shift toward the HI as the result of changing the volume of the container because we have 2 moles of gas on the left and 2 moles of gas on the right. So what else could you do to cause a shift? Well, you could not add more HI, but you could add more of the reactants. So one possibility would be, okay, you could add more hydrogen. Another possibility is you could add more iodine. And they did give us that it was an exothermic reaction with a negative delta H. So what you could have done is you could actually have decreased the temperature. Now, when you increase the temperature, it's always going to go in the endothermic direction, but this happens to be an exothermic process. So I would want to go from left to right, which means I want to actually lower the temperature, not raise the temperature, lower the temperature. So I've got 3 options. So looking at my scoring guidelines here, decrease the temperature or add more of either hydrogen or iodine. Now remember how I told you that equal number of moles of gas on both the left and the right? After equilibrium is established, it is transferred to a larger container. Normally, if you transfer something to a larger container, like if you go like smaller container, larger container, well, that would cause a decrease in the partial pressure of all of these chemicals. So we have partial pressure of iodine, partial pressure of hydrogen, partial pressure of HI. But because we have this particular expression with 2 moles of HI, so that'd be that number squared, divided by, then we have hydrogen and iodine, same number of moles of gas, there'd be no change. And so it says, as a result, would the number of moles of HI increase, decrease, or remain the same? It's going to remain the same, but your justification has to be very clear. You can't say something like, changing the volume would not affect any of the pressures, or the only thing that would change it would be, I don't know, change the temperature. Like, why is it going to remain the same? Because there's equal number of moles of gas on both sides of the equation. So that's really your argument. I'll go ahead and show you what it says on the official scoring guidelines, but same number of moles of gas on both sides of the equation. All right, remain unchanged. The number of moles in the numerator and denominator of either Q or K are equal. So that was the story. Or you could say, increasing in the volume will cause like Q to become equal to K. It's going to decrease the concentration. I shouldn't say pressure. It's really concentration because it's a Kc, but same idea. It's going to cause an equal value of Q. Q remains equal to K because you're going to like decrease everything by 1/2, but you've got 2 moles of HI and you've got 1 mole of H2 and 1 mole of I2. So whatever you're going to change, it's not going to change the value of Q. So equal number of moles of gas on both sides is kind of what was the deal. Now, let's take a look at sample student answer number 5. Okay, let me go find my commentary for sample student number 5. Again, first student got full credit. So they said, you know, stay the same since the concentration would decrease, but the numerator expression is squared. So yeah, that's great. All right, here we come to potential mistakes. I am happy with the Kc expression. So this student earned 2 out of 4 points. They definitely got the point in part A for the right K expression. In part BI, the point was not earned for drawing only 1 molecule of HI. In part B double I, nope, Increase in pressure, that's not specific. They didn't say add more hydrogen, add more iodine. So they did not earn the point in part B double I, because again, increase in pressure would not cause the HI to increase. And then finally, here's what they said. Number of moles would stay the same. Great. Let's see if their justification is good. Since volume would increase when the mixture was transferred to a larger container, that means that the pressure would decrease. Okay, cool. If the pressure decreases, the system would shift to the reaction toward the side of the reaction to try to create more gas particles. Since the number of reactant gas particles is equal to the number of product gas particles, moles would stay the same. So yes, they earned 2 out of 4 points. They got the point in part A for the correct Kc expression, and they lost the point because didn't have the right number of molecules. They lost the point here for not talking about this correct change that would cause an increase in the HI product. And then this was an acceptable justification for that. So they got all 4 of those. My next example student looks like they got only 1 out of 4 points. So they got this one. Too many molecules of HI. The temperature could be the experimental change. You didn't tell me how it was changed. So they were too vague and didn't specifically say temperature would be decreased. And then number of moles would increase because the volume is larger. And so, yeah, okay. All right, moving on to our next question in the 2024 free response. Okay, this is question 6. Looks like we have natural log of concentration versus time, and then we have 1 over concentration versus time. I like that graph on the right because it is linear. Explain how the graphs indicate that the reaction is second order. Okay, it's not about this. That's not why it's second order. It's because of this graph that is linear. So plot of 1 over concentration versus time. This would be, again, Unit 5, kinetics. So official scoring guidelines say the plot of 1 over concentration versus time is linear, indicating that it's second order. Okay, cool. I see a Lewis dot structure coming up here. At a certain point in the reaction, the rate of disappearance of NO2, okay, so let me go ahead and erase my drawing here so it's not all messy. Okay, the rate of disappearance of NO2, which is going to be the reactant, is determined to be 6.52 times 10 to the negative 7 molarity per second. What about the rate of appearance of O2 at the same point? Well, let's take a look at the stoichiometry here. This is not about first order, second order. It's simply going from one chemical to another within the context of the coefficients. So I see 1 mole of O2 is produced for every 2 moles of NO2 that are consumed. So the disappearance of NO2 would be twice as much as the formation of O2. I'm just literally going to multiply by 1/2 and use the coefficients to do that. So that's all they did. Ratio was 1 over 2. So that's how they used the stoichiometry and the coefficients to do that. All right, next point. Now, the one on the left is not something that you would have to draw on the AP Chemistry exam. The one on the left is not something you would normally have to draw on the AP Chemistry exam. Why? There's an odd number of electrons. You don't normally see single dots. Okay, so they did that for you. Now, going from NO2, which, to keep track of your valence electrons, that would be 6 for oxygen plus 5 for nitrogen plus 6 for oxygen. That's why that's there, okay? Whoops. That's why that's there. That's an odd number of electrons. What are we doing? We're going from an atom or a molecule to a polyatomic ion that has a positive charge. So we're going to lose 1 electron. That means that this structure has to have 16 electrons because this structure has 17. Let's start with single bonds. 2, 4, 6, 8, 10, 12, 14, 16. I just ran out of dots, but the nitrogen doesn't have a complete octet. I'm going to go ahead and turn that into 2 double bonds, kind of like carbon dioxide would have that same structure. So what they were looking for is that right there. And then the last part of that question says, a student makes the claim that the bond angles are different from each other. Well, yeah, one of them has a single dot on the central atom, which does cause a little bit of repulsion. Not a lot, but a little bit. And the other one is completely linear with two double bonds and no electrons on the central atom. So we have linear 180 and we have slightly bent. So I would agree with the student. Remember, you don't always have to disagree with the student claim. Like, they're not trying to trap you and say it has to always be disagree, disagree, disagree. Yeah, student makes the claim that their bond angles are different. If all you say is, I agree with the student's claim, that would not get you the point. Justify your answer. Talk about the bond angles in terms of the structural features. I would say because of the presence of a electron on the central atom, that would cause it to be bent, whereas there are no electrons on the central atom on the other ion, that would be linear. You could even say things like sp2 or sp if you want to talk about hybridization, but definitely the presence of that lone pair was the story. So agree with the student's claim. The angle is different because there would no longer be a non-bonding electron on the central atom. So you change it from something that's bent to something that's 180. Or, there it is, sp2 versus sp. Bond angle would be different. Okay, let's go ahead and take a look at the samples for student who'd answered question 6. Okay, so again, first student gets all 4 points. Let me go find my commentary. Okay, the student got 4 points. So here we come with, all right, so my commentary says that this particular student earned 2 out of 4 points. So in part A, the point was earned for correctly indicating that the 1/, concentration graph is linear. Looks good. They didn't recognize the 1:2 ratio there. They wrote the exact same rate of appearance. The point is not earned in part B because they didn't change that number at all. All right, in part CI, I don't see a complete octet. I see 2, 4, 6, 8, 10, 12, 14, 16. So right number of electrons, but the nitrogen has a double and a single. So nitrogen did not have a complete octet. But yes, I agree with the bond angles are different because you have an unpaired electron. So they did earn the point in CII for agreeing with the claim and providing a correct justification. All right, next point, next person earned 1 out of 4 points. Because it is decreasing exponentially in the natural log graph, that means it's second order? Nope. It's got to be the one that's linear, which is the 1/, concentration. Interesting. Good point I'd like to make here. In part B, the point was not earned, get this, for an incorrect calculation of the rate of appearance with no supporting setup shown, okay? Now, had they gotten the correct answer but didn't show any work, they would not have earned the point. So please show your work. Do not just report an answer with no work shown, especially for calculations. Always show the setup. It's really important. All right, in part C, there we go. That was the point that they earned, correct Lewis structure. They said, I agree, the bond angles would be different due to only one of the oxygen atoms having a double bond, while all of the bond angles in NO2 would be the same. So it's not about single versus double, it's about that presence of the electron on the central atom. So in part CII, the point was not earned for an incorrect justification. They thought the difference in bond angle is due to a difference in bonding rather than the presence of the lone non-bonding electron on the nitrogen. All right, we are now going to go to our final question of the evening. Again, I was thinking I might get through more than one free response question set, but I think we're going to stop with the 2024, okay? So if you like this style, all of these sample student responses are completely available to you. Okay, if I go down to the 2023 or the 2022, I can see all of these sample responses, and the commentary that I'm talking about is included in that. So that this is a great resource for you. Okay, so back to question 7 of the 2024 exam. Again, remember how I talked about the entry point being pretty simple for the part A? Calculate the mass of solid sodium chloride that is needed to prepare 100 milliliters of 0.34 molar sodium chloride. So that would be 0.1 liters times 0.340 moles per liter, and then times, let's see if I can do this math in my head. I think it's around 58.44 grams for every 1 mole. So that's pretty straightforward. Let's go see if that was the setup for part A. Okay, scoring guidelines say, just close some of these other documents. All right, there it is, 0.1 times 0.34 times 58.44. Now, I'm not sure if we need that number in part B. We'll find out. Oh, wrong question. So that was the answer to part A. Just do that calculation. In the following table, briefly list the additional steps necessary. Okay, so in terms of like lab procedures, I'll go ahead and I'll put in the video description area. I actually have a Google document that I'll share with you. It's got lots of AP free response questions that are specifically related to lab procedures and experimental stuff, but I will share that in the video description. It just reminded me that I think I have shared that recently in one of the YouTube comments, but I'll go ahead and put that. So this is an example of, do you know how to do the procedures? So I will, after this session ends, I'll put that link in the video description. That's a Google document that I created with all kinds of sample free response questions that are specifically related to lab stuff. All right. Use the weighing paper and scoop to measure the correct mass. Then you need to add the solid to a what? Not a beaker, not a graduated cylinder, not an Erlenmeyer flask, but a volumetric flask. So that would be a point for choosing the correct piece of lab equipment. And of course, then you're going to add some water to get that to dissolve. So add some water. Don't add all of the water. Add maybe like, I don't know, 50 mils or something. Make sure it all dissolves. And then carefully top off the volume by, adding water with a pipette until the final volume is even with the mark on the flask. Okay, so I'll just go ahead and show you what that says. My writing is getting rather illegible. Okay. So, oh, there it is. Sorry. Part B, combine the solid sodium chloride and some distilled water into a 100 milliliter volumetric flask. You don't say volumetric flask, you don't get this point. You say add all of the 100 milliliters of water at once, you don't get that point. But then you need to make sure that you fill the volumetric flask with distilled water to the calibration mark. That's how you prepare a solution in a volumetric flask. And then the last part, chromatography. A second student conducts the same chromatography experiment that we're seeing here, but they remove it after 15 minutes instead of after 30 minutes, which means if you run this experiment again, oh, that was terrible, sorry. The solvent front would not be here. It might be like right here. So if you're stopping it early, this is the solvent front. Well, now these two little components, they probably wouldn't have very much separation because you didn't run that chromatography all the way. So predict the effect it would have on the separation distance between the compounds X and Y. It would be less because it didn't travel up the paper as much. And so we'll go ahead and read what the official scoring guidelines say. It would decrease. The solvent front would not travel as far in the second experiment. So the separation would be smaller. All right, last sample question of the evening, or last sample student responses. Go find my scoring commentary and we'll see how many points these students earned. That's the official scoring guidelines. That's the official student who got all 4 points. So we're coming to, all right. This student got 2 out of 4 points. In part A, the point is earned for a correct calculation of the mass of sodium chloride. In part B, the first point was not earned due to not indicating adding the solid sodium chloride to the flask. Like, what? You go from weighing the sodium chloride on the balance to adding 100 mils of distilled water to the volumetric flask. You forgot to mention add the solid, and you obviously wouldn't add all 100 mils of water at once. Then it says that the second point was not earned because the volumetric flask is not filled to the 100 mil mark after dissolving the solid. And then, yes, they did get this point for saying that the mixture would not travel as far, so less separated. Now, again, make sure you answered the question. If you said it wouldn't travel as far, they're looking for less, as in, it says predict if the effect, if any, that this would have on the separation distance. If you never actually said the separation would be smaller and you jumped straight to because, make sure that you actually answered the question that's being asked and then go ahead and provide the justification. So sometimes students will skip to the justification and they forgot to say increase or decrease or something like that. All right, this next student earned only 1 point. Looks like all they got was the correct mass of sodium chloride. Beaker, no, volumetric flask. What? Okay, you know how to make a solution, or you should. The only effect would be the compounds would not have climbed as high on the solvent front, but they wanted to talk about the separation. So in part C, the point was not earned for failing to compare the distance between X and Y. So again, read the question carefully. Make sure you answer the question. All right, what I'm going to do now, since that was the last little part, I am going to switch over to camera only. All right. So what I will do, just making sure that camera is on. Yep, okay, cool. What I will do is I will put in the video description area of this YouTube video. I will put in the video description area a Google document that I have created. Oh, actually, one more thing I want to do before I'm going to go back to sharing my entire screen. Okay. I forgot to mention one more thing. In this Google document, there was something that I didn't talk about that I wanted to mention. It's right there. This is a great resource. So this is not something I created. You can see if you click on this article that is linked in the Google document, my teacher friend from Indiana, her name is Nora Walsh. She has this resource, which I think would be great for you all as you're preparing for the FRQ section. It's very specific to things you should say, things you should not say. Again, kind of related to the theme of tonight's presentation. So check that one out. I think it's wonderful. So again, this teacher, her name is Nora Walsh. She lives in Evansville, Indiana. This is a wonderful resource for what to say, what not to say. So I think that was a great thing. I just forgot to mention it, so I'm glad I remembered. Okay, now I'm going to go ahead and switch my camera. Let's see here. Okay, so I am very excited to have had the chance to share the 2024 AP Chemistry Free Response questions with you, but not just the correct answers, but examples of common students' mistakes. And again, you can find this on the College Board site. Okay, you can just look for past questions, official scoring guidelines, sample student responses. That would be a great resource. And so what I'll do is I'll put that thing I had mentioned in the video description area, which is a link to specific FRQs that deal with labs, measurement, and other types of experimental data. So again, I'll look in the video description area, and as well as the comments, I'll look at the comments. If there was something that you really were hoping for that didn't happen in tonight's session. But again, we're looking at, it's almost like an hour and 50 minutes. So I tend to be a long form video presenter, as you know, like from my videos. I mean, I don't have a problem going 2 hours or more. But I hope that you found all of these 7 free response questions, correct answers, common students' mistakes, helpful. So I'm going to say good luck studying for the AP exam. I hope you will do well. And again, read the question carefully, answer the question that's being asked, get as much detail into your responses, and pay attention to all of those things, like justify your answer in terms of show your work for calculations. Go check out my link to the Google document that I will put in the video description area on lab-based FRQs. Check out the resource I mentioned from Nora Walsh in terms of write this, not that. And yeah, get some good rest tonight. So don't stay up till 2 or 3 in the morning. Hope that this session was helpful. Thanks for watching, and I will end our session. So good luck. Bye now.